Now we need to look at how to balance equations to make sure that they follow the law of conservation of mass. So according to the law of conservation of mass, no matter is created nor destroyed during the course of a chemical reaction. What's simply happening is the bonds of the reactants are broken, the atoms are being rearranged, new bonds are being formed in order to create the products. So no atoms are created, no atoms are destroyed, they're simply being rearranged to transform the reactants into the products. So sometimes when you write a skeleton equation, it's going to follow the law of conservation of mass, but other times the law of conservation of mass is not going to be followed when you write that skeleton equation. So for example, when I'm looking at aluminum plus bromine yielding aluminum bromide, it's not following the law of conservation of mass at this point. There's 2 bromines on the reactant side, there's 3 on the product side. You couldn't make a bromine during the course of the chemical reaction like that, an atom like that. So now we need to go through and fix this chemical equation in order to make sure that it's balanced. So a balanced equation shows equal numbers of atoms on both sides. In order to make a chemical equation balanced, you need to add coefficients in front of the formulas of the reactants and the products. So a coefficient is a large number that is placed in front of the formulas of the reactants and the products. And what a coefficient does is it multiplies everything in the formula that it's placed in front of. So what I now did was I added coefficients to that equation to make sure that it was balanced. So now I have 2 times 1, 2 aluminums on the reactant side, 3 times 2 bromines, I now have 6 bromines on the reactant side. When I'm looking at the product side, I have 2 times 1 aluminums, I now have 2 aluminums, 2 times 3 bromines, I now have 6 bromines on the product side. So both sides have equal numbers of each type of atom present. Key things about coefficients, they're whole numbers. They can never be written as a fraction or a decimal. If the coefficient is a 1, it's left blank. And just make sure that coefficients need to be the lowest whole number ratio possible. So if you can reduce the coefficients down, make sure to also reduce them down. All right, so now I want you to go through and answer the 2 check for understanding questions. The first one asks you to reduce the coefficients in this chemical equation. So we have a 3, a 3, and a 6. That reduces down to a 1, a 1, and a 2. Notice how I didn't write the ones. By leaving the ones blank, it implies that the coefficient is a 1. So for B, it's asking you to determine the total number of elements. So what you need to understand is that 2 is multiplying everything inside of the parentheses, but then that 4 multiplies everything in that formula. So we have 4 leads, 8 nitrogens, and we have 24 oxygens. For this next one, that 2 outside the parentheses is multiplying everything inside of the parentheses, but then that 2 coefficient multiplies everything in that chemical formula. So we have 4, 16, 2, and then 6. So now let's start to go through and look at how to balance chemical equations. So what I'm going to do is I'm going to model examples, and then you'll attempt to kind of balance some with the check for understanding problems. There's different methods for balancing. You need to figure out what works best for you. The key thing is you're able to produce the correct coefficients to make sure that that law of conservation of mass is being followed. All right, so the first thing that you're going to do is you need to make sure that you have the correct skeleton equation. Then you're going to create an inventory that shows all of the different elements that are present on both sides of the chemical reaction. So I have sodium, chlorine, calcium, iodine. Notice how I kind of line them up. So I'm going to be able to kind of compare the inventories on each side easily. Now I'm going to go through and figure out how many of each atom is present. There's 1 sodium, there's 1 chlorine, there's 1 calcium, and then there's 2 iodines on the reactant side. On the product side, I have 1 sodium, 2 chlorines, 1 calcium, and then 1 iodine. Now I'm going to start to add coefficients until I'm able to get both sides to have equal numbers of each type of element. So there's two things that I could start trying to balance first. I either have chlorine or I have iodine. Let's say I start by trying to balance the chlorine. I'm going to place a 2 in front of sodium chloride. That then multiplies the number of chlorines. So now I have 2 on the reactant side, but it also affects the number of sodiums. I now have 2 times 1. I now have 2 sodiums on the reactant side. That coefficient alone was not enough to balance the equation. I now see that I have sodium. It's not balanced. So let me see what happens when I place a 2 in front of sodium iodide. Now 2 times 1 sodiums, I now have 2 sodiums on the product side. 2 times 1 iodine, that brings the number of iodines up to 2. So now when I'm looking at both sides for that inventory, I have 2 sodiums on both sides, 2 chlorines, 1 calcium, 2 iodines. It's now a balanced chemical equation. Sometimes you might need 1 coefficient to be enough, sometimes 2, sometimes 3, sometimes every single thing needs a coefficient. It just varies depending on the reaction that's taking place. All right, so now you can go through and try to balance this equation. So you would go through, do the inventory. You can balance oxygen first by putting something in front of that reactant. That now is going to multiply the number of oxygens on the reactant side, so you have 2. You're now also going to have 2 mercuries, but now I need to go to the mercury on the product side and place a 2 in front of it in order to make sure that it's balanced. So the correct coefficients, I need a 2, and a 1, but that 1 is left off. I don't write it. It's implied that it's a 1 by leaving it blank. All right, so next one, you're going to go through and try to balance this one. Why I included this is to kind of show you that sometimes the element you start balancing first affects how hard or how easy the problem is to solve. So I would go through and I would do my inventory. Let's say I'm going to try to balance sodium. So I'd put a 2 in front of sodium. That means I now have 2 sodiums on the reactant side, but now I would need to add a 2 in front of sodium oxide in order to change the number of oxygens on the product side. So now I have 4 sodiums and 2 oxygens on the product side. Now I need to go back and erase the coefficient of 2 that's in front of sodium on the reactant side and change that to a 4 in order to make this a balanced equation. So this took me about 3 steps. I had to change a coefficient in order to balance it. Now let's kind of wipe everything clear and look at what happens if I balance oxygen first instead. I would place a 2 in front of sodium oxide. That would bring the number of oxygens up to 2 and sodiums up to 4. I would place a 4 in front of sodium and then I would be done. So you can see it took less steps. I didn't have to change any coefficients a second time. So just understand sometimes the element you start balancing from first can affect how hard or how easy the problem is going to be. So if you're sitting there and really struggling to balance something, sometimes it's good to just start over and pick a different element to start balancing from first. All right, so you can go through and try to balance this one. So I go through, I do my inventory, I go through and I notice that I have 2 chlorines on the reactant side, I have 3 on the product side. They both have 6 in common, so I'm going to try to get both sides to have a total of 6. Let's say I put a 3 in front of zinc chloride. That brings the number of chlorines up to 6, the number of zincs up to 3. On the product side, if I put a 2 in front of aluminum chloride, that brings the number of chlorines up to 6, the number of aluminums up to 2. In order to finish this problem, I place a 2 in front of aluminum. That's going to balance the aluminums. I put a 3 in front of zinc, and now it's a balanced chemical equation. Now what I want to model for you is how to balance chemical equations when you have the same exact polyatomic ion on both sides. This method helps simplify balancing these types of reactions where you have the same polyatomic ion on both the reactant and the product side. So normally when we did the inventory, we broke it down by individual element. But what we're going to do is we're going to keep that polyatomic ion as a whole unit. So I have aluminum, I have nitrate, I have sodium, I have sulfur. On the product side, I'm going to have those same exact things. So I didn't break nitrate down into nitrogen and oxygen. I left it as a whole unit. It appears on both sides. So I go through and I do my inventory. I have 1, 3, 2, 1. I have 2, 1, 1, and then 3. So now let me try to balance aluminum first. I place a 2 in front of aluminum nitrate. Now I have 2 aluminums, but it multiplies the number of nitrates up to having 6. Now, if I place a 6 in front of sodium nitrate, now I have 6 nitrates and I have 6 sodiums. If I place a 3 in front of sodium sulfide, that brings the total of sodiums up to 6 on the reactant side and sulfurs up to 3. So now I have the balanced chemical equation. This method only works if the same exact polyatomic ion appears on both sides. So now what I would like you to do is try to balance this equation, but use the method of keeping the polyatomic ion as a whole unit in the inventory. All right, so when I go through and I do my inventory, I have 1 aluminum, I have 2 hydrogens, and I have 1 sulfate. On the product side, I have 2 aluminums, I have 2 hydrogens, and I have 3 sulfates. Let's say I go through and I place a 3 to try to start to balance the number of sulfates. That now brings the number of sulfates up to 3, but now that also affected the number of hydrogens. Now I have 6 on the reactant side. So now if I go through and I place a 3 in front of hydrogen on the product side, that brings the number of hydrogens up to 6. The only thing left for me to do is place a 2 in front of aluminum, and now I have a balanced equation. So this method only works when the same exact polyatomic ion appears on both sides. Now you're going to tie all of the skills we've learned together by solving this problem. So you're going to take that description and write a complete balanced equation. So my first step is I'm going to write the word equation. Then I'm going to take that word equation and convert it into the correct skeleton equation. So iron is by itself, it's not diatomic, so just write Fe, it's in the solid state. Chlorine is by itself, it's one of the 7 diatomic elements, so it's Cl2, it's a gas. And then for iron 3 chloride, it's ionic, so I crisscross to get FeCl3, and it's in the solid state. Now I'm going to go through and I'm going to balance it. So I see that this skeleton equation does not follow the law of conservation of mass. Now we know how to fix that issue by adding coefficients to create a balanced chemical equation. So I go through, I make my inventory. What I'm going to do first is I'm going to place a 3 in front of chlorine on the reactant side. That brings the number of chlorines up to 6. 3 times 2 is 6. I place a 2 in front of iron 3 chloride on the product side. That brings the number of chlorines up to 6. 2 times 3 is 6. But it also changes the number of irons. So now I have 2 irons on the product side. To finish this equation, I'm going to place a 2 in front of iron on the reactant side. And now I have a balanced chemical equation.